Hi, and welcome back to our videos about determinants. In this video, I'm going to summarize and show you the most important methods for computing a determinant. To keep it short and to the point, I'm going to give you examples for all of these methods in a separate video. So, this is called computing a determinant. And it's going to be a summary of rules for actually evaluating a determinant. You probably know some of these rules already, maybe you don't know others. Of course, as I said, there will be examples, but they will be deferred to a different video. So let's first recall the general formula. Of course, that can also be used as a means of computing a determinant. And the general formula was the determinant of A, of a matrix A, is given by the sum over the i's here, minus 1 to the power of I plus 1, times AI1, so the entry in row I, column 1, times the determinant of the I1 cofactor. And one special case, the determinant of a 1 by 1 matrix is defined as simply the entry itself, A11. You will remember that we have already applied this to a 2 by 2 matrix. So let me list that once more. So we have a 2 by 2 matrix that looks like this: A11, A12, A21, A22. And you remember we computed the determinant of that by first multiplying the entries here along that diagonal, and then multiplying the entries along this diagonal here. And we counted the first part with a plus, and the second part with a minus. So in other words, what we have here is A11, A22 minus A21, A12. So that's the simple rule for 2 by 2 matrices. There is a similar but a little more complicated rule for 3 by 3 matrices as well. Let me list those here as well. So a 3 by 3 matrix. That rule is known as Sarou's rule. And again, the idea is just to apply the general formula that we've learned about and then rearrange the resulting summands in a clever way, so we can make up an easy visual rule of how to compute that matrix or that determinant. Now let me write that down. So the determinant, we want a determinant of a matrix A11, A12, A13, A21, A22, A23, and A31, A32, A33. So that's the determinant that we want. And now the idea here is to copy the first two columns and write it behind the actual matrix once again. So we copy that first column, A11, A21, A31, and then a second column, A12, A22, A32. And then we can apply a rule that is similar to the one that we've used before. More precisely, what we do is we again take the diagonal, this one here, And then also the two diagonals above that. And that's where we need those copied columns. This and this. And again, we count these as positive. So we multiply the product, we multiply the numbers along each of those diagonals and sum up all the results with a positive sign. And again, similarly to what we did with the 2 by 2 matrix, we'll then take this diagonal here and the next two below that, like this. And we'll add those with a negative sign. So there's a minus here. And this gives us a determinant. So what we get here is product of this diagonal. So that's A11, A22, A33. Plus the product along this diagonal. That's A12, A23, A31. Plus the product along this diagonal here. That would be A13, A21, A32. And then we have a look at the negative diagonals, this one first. So we subtract that, minus A31, A22, A13. Then this one, again subtracted, so minus A32, A23, A11. And last but not least, this one here, minus A33, A21, A12. So that gives you a formula for 3 by 3 matrices, and this is actually very important. This formula can only and exclusively be used for 3 by 3 matrices. I cannot stress this enough. Do not use that formula for matrices of higher order. This will not work. It will give you a wrong result. So please, this is only for 3 by 3 matrices, for nothing else. Okay? So, I'd say these are probably the most well-known ways of computing a determinant, but there are others. And we'll have a look at some more right now. One particularly easy way of computing a determinant is if we have a matrix in triangular form. So that means if we have a determinant of a matrix that looks like this, A11, A22, and so on the diagonal up to A and N. Below those, we'll only have zeros, like this. And above, we're allowed to have anything we want. So basically what we have here is a matrix in echelon form, and that's what makes it so important, the special rule here. Now if we have a situation like this, then the rule is very simple. If we apply that formula for the determinant, what we get is A11 times the 1,1 subfactor, cofactor, that's this one here, plus lots of zeros. And we can apply the same rule to the 1,1 cofactor again, and we get this element times this cofactor, and so on. So in the end, what we will have is A11 times A22 times A33, and so on, up to A and N. So in other words, this is the product of the diagonal entries, AII. So if the matrix is in this form, then the determinant is immediate. You just multiply all the diagonal entries. But you need to have zeros here below. That's why it's called triangular form. Now, of course, that doesn't seem very useful because how often do you get matrices in triangular form? But it is if you combine it with those results on row operations. Remember, we can apply row operations without changing the determinant or without changing much. We may change the sign, we may change a factor, but that way we could basically apply Gaussian elimination to those matrices to bring them into echelon form. And echelon form also means we have triangular form here in a quadratic matrix. And that is easy to see the determinant. So we can just extend that method by using elementary row operations. And that's something that I often use for very large matrices because we know how to do these row operations. We have practiced them over and over again. So I can be pretty sure we won't make too many mistakes applying these. And that gives us an easy way to obtain the determinant of a matrix. So basically, let me sum up what we did there. What we can do there is, remember, we can do a row exchange. If we do this, the sign changes. We can add a multiple of one row to some other row. If we do this, the determinant does not change at all. And finally, we can multiply a row by some factor lambda. And if we do this, the determinant also changes by that factor lambda. So that's probably the most complicated one. So I try to avoid that last operation, but the first two will usually get you where you want to be. So the idea is to use row operations to obtain triangular form. And in quadratic matrices, this is the same as echelon form. And then we just use the method above. Okay, so that's a method that is especially suitable for very large matrices. And of course, you can also use this as kind of a pre-processing if you want to. Yeah, so you can use some elementary row operations to make the matrix easier and then use some other method. Usually making the matrix easier means introducing as many zeros as you can, because zeros always make the computations easy. And that's especially true if you are going to use the last method that I'm going to talk about. That is called Laplace Expansion. And basically, we did this already. You remember that we defined the determinant in terms of the first column. Now that first column is really not that special after all. Because of course what we can do anytime you want is we can transpose the matrix to exchange rows for columns. So we could equally well use the first row. And once we're talking about rows, you know, we can exchange any two rows. That will change the sign, but that's it. We just have to pay attention to the sign change. So we can put any row we want into that first place. And that basically means we can do the same or almost the same formula for every row or every column of the matrix. So how does this work then? If we have a matrix A equals Aij, n by n matrix, then there's two possibilities. We can either use a row or a column to perform the Laplacian expansion. I'll list both formulas for your convenience here. So let's say we want to do expansion with respect to the ith row. Then that formula that we had in the definition changes a little, but just a little. So again, we have a sum. I'll call the index k here because I is used for that ith row already. And basically we sum up over all the entries in that ith row, just as we did for the first column. We have a sign that is determined by -1 to the power of row plus column. So this here is the row. This here is the column number of that current entry. We multiply that by the current entry, so that's a I for ith row and k for kth column. And then multiply by the determinant of the corresponding cofactor, a, I, k. Again, this is the ith row and the kth column. So same thing as we did for the first column, just apply to a row now, and of course the cofactors will look a little different, but the idea is totally the same. And we can of course do the same thing for the columns. So expansion with respect to the jth column. That formula looks almost the same. That is, determinant of A is then the sum of. So this time we sum up over all the entries of that jth column. Again, we have a sign, and again, the form of that sign is kth row plus jth column. So in the original formula, that j was 1. That was where this k plus 1 came from. Times the entry in that position, so that is kth row, jth column, times again the corresponding cofactor, that is a, k, j. So you delete the column and the row of that entry and take the determinant of the resulting smaller matrix. I'll show you examples for all of this in one of the next videos. So hopefully this expansion rule will become a lot clearer once you see it applied to an actual matrix. And I'm confident I'll see you then.